ladies and gentlemen, hello, welcome. Coming to you not quite live from One Take Studios, where today we are talking about rational functions. This is not like rational versus irrational. This is like rational as in fraction, as in everybody's favorite stuff. Alright, we've got a lot of in-depth information about rational functions today, and we are focusing largely on graphing and what it means with the different parts to create something that's good for graphing. Alright, so that's ratio part of it. Okay, we are going to focus on two types today, and this is going to be our first type. Alright, so two types of rational functions, two structures basically, and this is going to be what I consider to be the easier of the two. F of x is equal to a over x minus h plus k. Ladies and gents, I'm hoping you've got some sort of thing going on in your brain with like, ooh, h, k, I've seen those before, a, I've seen those before. You have. If you've done anything with transformations of graphs, you have seen these same letters. And the patterns still exist. They do the same thing. Alright, A controls stretches and compressions and reflections. H affects the x value. That means that H controls left and right movement. K is what we tack on to the final total. That means the outcome. That's the y value. So K slides us up and down. And so having all of those things in mind can be very helpful with what we're looking at today. Alright, so very specifically for the moment, I want to look at the parent function for this. I cannot get any more simple than 1 over x. Everything else is an alteration on 1 over x. Notice a is a number. So this is how you're going to identify this first type of rational function, is that the top has a number and a number only. You will not find variables in your numerator right now. Okay, so this is 1 over x. So let's think about this. What can we not divide by? Oh, that's right, we can't divide by 0. That means for this graph that x cannot equal 0. If x cannot equal 0, that means that x can never equal 0. That means that x equals 0 is actually located on the y-axis, and there is going to be an asymptote, so there's going to be absolutely no value whatsoever for this graph on the y-axis, creating a vertical asymptote, a line that the graph will continue to approach, but right now is not going to actually touch it. So, okay. Now, that's usually more okay with people. Let's look at something that might be less okay with your brain. We know the input, the x value, can't be 0 because I can't do 1 divided by 0. What would it take for the output of this graph to be 0? What would it take for this fraction to equal 0? The y value to equal 0? Well, in order for a fraction to equal 0, that means that you have to have 0 on top. We have a 1 on top. What's the likelihood that we're going to have a 0 on top if there's a 1 that's already there? Okay, it's not happening. So, in addition to a vertical asymptote, we also are going to be having a horizontal asymptote, which is on the x-axis this time, because y cannot equal 0. So I cannot put 0 into this function, and there's no way for me to get 0 out of this function, so I have both a vertical and a horizontal asymptote, essentially dividing my graph space into a few different pieces here, and that's going to be kind of the key to this. This is pieces parts. Alright, most of the graphs you've probably done are continuous graphs, where you can put your pencil down and do one line or one curve or a set of curves, and you can graph the whole thing without picking up your pencil. Not true. This is a discontinuous graph today. I'm going to switch over to my calculator screen, and ladies and gents, that is what it looks like. That's our parent function. We can see that the x-axis has no value on it. It's an asymptote. So this piece of the graph approaches it from the top side for all of eternity, and this piece of the graph approaches it from the bottom side for all of eternity, but there is no actual value at y equals 0. Also, the vertical right there, y-axis, is also an asymptote. This piece approaches it from the left for all of eternity. This piece approaches it from... I'm going to breathe. Approaches it from the right for all of eternity. Gets closer and closer, but again, we have no actual values there. So this graph has two pieces. They're referred to as branches. All right, so I've got a branch over here, I've got a branch over here. They are not connected to each other, but that is one graph. It is called a hyperbola. Not to be confused with hyperbole from the English, but hyperbola. Okay, dokie. Now, everything else, like I said, is going to be a change from that. So what happens if we decide to play with that? What happens if we move it? All right, I'm going to go back to my other screen. There we go. Okie dokie, where I have a graph page for you here. Check it out, ladies and gents. Okay, we are talking g of x equals 1 over x plus 3 minus 2. Again, this is of that type 1 format because I have a number on top and then x minus h plus k, number on top, x minus h plus k. So what does this mean as far as asymptotes might be concerned? Well, I can't divide by 0. That means that there's something here that's problematic, yes? I know that x cannot have a value of -3. That means that x equals -3 is a vertical asymptote. An asymptote is a place where you cannot go, and I cannot go to -3. Well, this thing also had a horizontal asymptote on the x-axis, and k controls up and down movement of the graph. So if I had an asymptote here at 0, and I move everything down 2, I'm now going to have a horizontal asymptote at -2. So when I go to graph this thing, -3 for the x, 1, 2, 3, right here is going to be my vertical asymptote. At -3, this is where my graph cannot go vertically. And then right here, because everything got moved down 2, what was the x-axis is now here instead, and I have a horizontal asymptote at -2. This kind of becomes my new set of axes, sort of, for the purposes of graphing. You're going to get a symmetrical set of branches again, but this time instead of having them be in the first and third quadrant, they're going to be spaced out between my asymptotes instead. All right, so I'm going to do this real quick too, and then I'm going to go to the graph and we'll take a look at it. Please understand that this right here, the reason I put domain and range next to asymptotes is because a lot of people do get this confused. Okay, so if we are looking at the domain for this graph, what are the x's? Well, my domain are going to be the x values such that, I'm using our formal writing here, domain are the x values such that, we're talking set notation. X can be anything in the world except x can't go here. So x can't be -3, so x cannot equal -3. So my x's are the set of numbers x such that x can't be -3. So x equals -3 is my asymptote because that is where the x cannot go. This one is equals, this one is not equals. What about my range then? My range, we're talking again the set of numbers y such that, well, what do I know about my y's? My y's are going to be able to be anything except I can't have a value here where y is -2, so therefore y cannot be -2. This is my asymptote. This is stating where the y values cannot be located, and so when I see that in my domain and range, y cannot be -2. All right, let's take a look at what that would look like, shall we? Let's switch screens again, go back to the other one. Here we are, and let's check out this next page. Ladies and gents, that's it. Which, if you thought about where we were placing those new asymptotes, it kind of makes sense that we can see that. If I'm going to graph this on paper, I do want to make sure I know where the asymptotes are located, and I also probably want to pick up a few points. If you have an Inspire, hit Control-T for Control Table, and you can get some lovely points for your graph. I would recommend roughly 3 points per branch. So let's see, what might I use here? I'm going to use what I see here. So at 2, I'm at -1.8, 2, -1.8. I'm sketching these on my graph. I'll go back to a second. At 1, we're at -1.75. Again, these are decimal numbers, so these are going to be not perfect in my graph, but darn close. At 0, I'm at -1 2/3. Oof, goodness gracious. Yeah, definitely not great for my graph here. 1 2/3, let's call that about there. So I've got a lot more points than I need at this moment. I'm going to keep going though. -1, -1 at 1.5 negative. Okay, keep going, keep going, keep going. What else do we have? At -2, I'm at -1. -2 is at -1. And I do know that at -3, I am undefined, which makes sense because we said that's one of our vertical asymptotes. At -4, however, we pick up values again. At -4, we can be at -3. So I'm going to get that guy in place. And at -5, I'm at -2.5. 1, 2.5, and so on and so forth. So negative 2 and a 3 right there. Okay. That's enough points that I'm going to go back to my other screen and show you what I wrote. And there we go. You can kind of get the feeling for where these things are located. The symmetry for this branch and this branch is absolutely going to be there. I'm going to go ahead and sketch. I know that this piece is approaching the asymptote, and this one is approaching the asymptote from this side. Got a whole lot of points there. Arrows at both ends, because that does keep on going, whoops, forever and ever and ever. And then same kind of thing here. I'm going to turn this way around because I draw better from this direction. Pulling this over here. All right, so again, I've got two branches. I have to draw them separately. They are not attached to each other. I cannot cross negative 3. I cannot cross negative 2, but these branches will be getting closer and closer to those asymptotes. Arrows at both ends because they keep on going. All right, so that is a lovely graph for such things. Okay, now, that was the easy one. What does that mean about our more interesting graph? Well, it is more interesting, I'll give it that. All right, so here's the other type. Type 1 had a number on top. Type 2 has a polynomial on top and a polynomial on the bottom. So the second type of hyperbola that we can graph, a rational function here, is that I've got a function on top and a function on the bottom, essentially. So I have a whole bunch of data here. Actually, I'm going to pull this back. This is a lot to look at one time. All right, so bits and pieces here, folks. Vertical asymptote. Again, should make sense. I know that I cannot divide by 0. So if there's any number on the planet that would cause my denominator to equal 0, that's going to be where my vertical asymptotes are located. And I did say totes because it's possible that you have more than one number that will make your denominator 0, so it is possible to have more than one vertical asymptote. Scary but true. Deep breath. Star number 1. Oh my gosh, right here, this piece right here, star number 2, star party zone, decorate this. Ladies and gentlemen, everything about the horizontal asymptote you need to pay attention to, because the first thing that's going to slide out of your brain as soon as this video is done is this next block of information. It does not stay in your head naturally, which means you've got to know that it exists and you've got to go looking for it in your notes when you need it. All right, we have different things that could happen. Of these two polynomials, which one has the higher degree? Well, if the higher degree polynomial is on top, that means that there actually will be no horizontal asymptote. So if the higher degree is on top, that's no horizontal asymptote at all whatsoever. You graph enough of these, you start to see it, patterns emerge. This is one of those patterns. Okay, what if the higher degree polynomial is on the bottom? If you don't know what higher degree means, I'm going to go through some examples here in a second to clear that up for you. If the higher degree polynomial is on the bottom, we do have a horizontal asymptote, and that is going to be located right here at y equals 0. Y equals 0, also known as the x-axis. All right, so what's the other thing that could possibly happen here? Higher degree on top, higher degree on the bottom. Ooh, what if I have the same degree polynomial top and bottom? What if they have the same degree? This is everybody's least favorite, although I really don't think it's that bad. It looks hideous, but we are saying that you will have a horizontal asymptote located at the location of the leading coefficient for the numerator over the leading coefficient for your denominator. If you have no idea what those words mean, again, I'm about to do examples to clear that up, but this is just making a fraction. I'm taking a number from the top polynomial over a number from the bottom polynomial. We can do this. I promise you we can do this. All right, so again, in case you can't tell, there's a lot of focus on the asymptotes. These are what set the boundaries for the graph, so it's really important to know where they are so that you can get a decent graph. Your table in your calculator can give you all kinds of points, but these are important to know. I would know them, I would be looking for them before I ever hit any buttons on the calculator. All right, so one last piece of information that can be useful for graphing as well is this guy right here. All right, knowing where your zeros are. Zeros, if you remember, are x-intercepts. So if I know where my x-intercepts are, these are kind of nice as well. Well, what's going to make this equal to 0? That's anywhere the numerator equals 0. So anything that makes the top equal to 0 gives me a 0, because it makes the outcome 0. That's an x-intercept. Anything that makes the bottom equal to 0, that's a vertical asymptote, because that's something we can't have, and that's someplace we can't go. All right, you got those, right? You got those there? Okie dokie. Ladies and gents, let's do some compare and contrast here, shall we? I have 3 examples, and we're just going to go through them one at a time. I'm not going to do a full graph. I'm just going to do a brief sketch for this stuff, okay? So, looking at this guy, f of x equals x squared minus 3x minus 4 over x. How do I know this is not the first type of rational function? Because I do not have a number on top. I have a polynomial on top, and I have a polynomial on the bottom. So this is absolutely type 2. And I want to piece together some of these elements here. So things that I may or may not know. You know what? I'm going to rewrite this, and I'm going to factor the top. So that's going to be x minus 4 and x plus 1, and that is over x. Why does this help me? Well, if I'm looking for where the top is equal to 0 or where the bottom is equal to 0, having these factors is actually going to be really useful. Yes, I do like that. Okay, so things that I know. Well, okay. Where does the top equal 0? If the x was 4, the top would equal to 0. So 4 is one of my zeros. If x was negative 1, the top would equal 0. So negative 1 is one of my zeros. So because that is where the numerator equals 0, I know that 1, 2, 3, 4, this is going to be a 0 or an x-intercept, and negative 1, this is going to be a 0, otherwise known as an x-intercept. What about the asymptotes? Okay. As far as vertical is concerned, what would make my denominator equal to 0? Well, 0. So at x equals 0, we have a problem. If x equals 0 is a problem, that means that I'm going to put this right next to it, but technically it's right on top of that y-axis. That is going to be one of the asymptotes for this. So I'm going to have a piece on this side, I'm going to have a piece on this side, asymptote running here. That's x equals 0. How about horizontal asymptotes? Okay, this is this big block of information. The degree of a polynomial is its highest power. So if I look on top, the highest, biggest exponent I see is 2, and on the bottom, the degree, the highest power is 1. So I have the higher power on top, lower power on the bottom. Higher power on top, higher degree here. That means that there is no horizontal asymptote. That's it. I just have the one asymptote right there. And again, I can put that in the calculator, I can find additional points, but this is going to be an important point, this is going to be an important point, and the asymptote is critical for getting everything in the right place and setting your boundaries. That was so much fun, we should do another one. Well, if you insist. Okay. So, ladies and gentlemen, going on to round 2 right here. So we have x minus 2 over, I'm going to, again, rewrite this because I can write this in a factored version. If you haven't noticed, factors are useful to us, so if you can factor, you should factor. That's x squared minus 1, that's difference of squares. That's x plus 1 times x minus 1. So, things that I know. Zeros occur when the numerator is equal to 0. What would make the numerator equal to 0? 2. What does this mean? This means that at 2, we will have a 0 or an x-intercept. There we go. As far as where my denominator might equal 0, again, this is getting me my vertical asymptotes. Well, what can I have or not have for x? X can't be negative 1, x can't be positive 1. Because if x were negative 1 or positive 1, we would have 0 in the denominator, which is terribly illegal. So at x equals 1, we have a problem, and at x equals negative 1, we have a problem. So here is x-axis, here is negative 1, we have a problem, we have an asymptote, cannot cross that line. And then at positive 1, there we go. There we go. So again, this graph is actually going to have 3 pieces instead of 2. There's going to be a piece on the left, there's going to be a piece in the middle, and there's going to be a piece on the right. Graph it, throw that in the calculator. I'm not going to do that for you today, but please, by all means, take a look at it, because it's fascinating. What else do we know? Well, does this thing have a horizontal asymptote? Consult your notes. You probably don't have this memorized. I usually don't have this memorized. What do I see? The degree on top is 1, because that's the highest power. The degree on the bottom is 2. Because that's the highest power. So the higher degree is actually on the bottom, which means I'm right here, higher degree on the bottom, y equals 0. Y equals 0 is also an asymptote. So this one has 3 asymptotes. Where does y equal 0? That is the x-axis. So again, I'm going to kind of put it right here, but I know that some of you are kind of going crazy right now. Hold on. My brain is processing life for a second. I do mean that. Okay, so some of you are going, hey, how can we possibly have a 0 at 2 and yet have no values there? Okay, you know how I keep saying that the asymptotes are places that the graph gets closer and closer but doesn't cross typically? Typically that's true. Occasionally you can have a graph that crosses an asymptote, because the pure definition of an asymptote is a line that the graph approaches for all of eternity. Occasionally, those will actually pass over the asymptote and then continue to approach it for all of eternity. So yes, technically you could have a 0 on an asymptote. That's going to be a crossing point, and again the pieces of the graph are going to continue to approach this line at the ends. Graph that. It's interesting. You should look at it. Alright, last one, I promise. Trying to get us one of each here real quickly, one of each. Okay, so last dude over here. What can I do with that one? What can I do? Can I factor? I can pull the 4, so let's take a look at that. That's going to be 4 times x minus 3 over x minus 1, x minus 1. Do I have any zeros? Is there anything that makes the top equal to 0? Yes. 3 would make the top equal to 0, therefore 3 is a 0, otherwise known as an x-intercept. What about asymptotes? Well, vertical asymptotes. I know that x can't equal 1, because if x were to equal 1, that would be problematic. That would make my denominator equal to 0. So here's the x-axis, here's 1, and this is going to give me a delightful vertical asymptote right there at x equals 1, because x cannot equal 1, therefore my graph should not be going there. Alright, I am then, okay, back. Are you looking? This is the one that people typically don't like a whole lot, but quite frankly, I think it's not bad. The degree on top is 1. That's the highest power. The degree on the bottom is 1. That's the highest power. I have a degree of 1 on top and a degree of 1 on the bottom. Same degree, top and bottom. What am I now looking at? Alright, look at your leading coefficient. Leading coefficient means the number in front of your variable with the highest power. In this case, it's 4. What about the leading coefficient here? Well, I don't see a number. Well, if I don't see a number, it must be 1. That's going to be the coefficient for the x. So, right here, leading coefficient over leading coefficient. Right here, that is my horizontal asymptote. Leading coefficient over leading coefficient, 4 over 1. So therefore, y cannot equal, what's 4 over 1? Well, that's just 4. There we go. That means that at 1, 2, 3, 4, I have a delightful horizontal asymptote here at 4. Alright. There's a lot of information here, a ton of stuff. Be patient. Consult your notes. You will not remember all of this at once. That's okay. Use the calculator, but please use your brain, because calculators without brains are dumb. Okay. Have fun. Enjoy.